Chapter 5, Atmospheric Circulations, Part 3. Here we'll look at semi-permanent highs and lows, or highs and lows that are created thermally, also the seasonal changes in global circulation, including monsoons. The effects of heating and cooling. How does heating and cooling of the atmosphere change the surface pressure? Well, we already know the answer from our discussion on thermally direct circulations. If you have a hot anomaly, a warm air column, that tends for the pressure surfaces to rise over that. That means you'll have high pressure aloft and air trying to evacuate that area towards lower pressure aloft. That means you're removing air molecules from the warm column, and that's going to reduce your surface pressure in that area. So again, low surface pressure develops over areas that are relatively warm. Areas that are relatively cold have compressed air columns, meaning that the pressure surfaces must fall aloft, giving you lower pressure aloft. Air wants to come in or converge from higher pressure outside that zone towards the lower pressure aloft, causing a piling up of molecules, increasing your surface pressure over relatively cold anomalies. This is just showing the circulation that will develop as a result of these hot and cold anomalies. At the surface here, you have low pressure for the reasons described. Air will then rise up throughout that warm column, evacuate the higher pressure aloft, and then sink down in the relatively cold column and return the circulation, giving you rising air, causing cloud formation over these warm, low pressures at the surface. This, of course, goes the other way when you're talking about surface highs. A surface high created thermally caused low pressure aloft. Air converges into that region that gave you the high pressure at the surface. That air converges and then comes down the column. As it comes down, its relative humidity must decrease as a result of the warming due to the compression, and then it evacuates the high pressure at the surface, completing the circulation. So the cold anomaly, the high pressure at the surface, is associated with sinking air, whereas the hot anomaly, the low pressure at the surface, is associated with rising air and clouds. Here's looking at July, the semi-permanent lows and highs around the planet. The first thing I want to point out, this is summer in the northern hemisphere, the oceans are relatively cold compared to the surrounding land surfaces. Therefore, you get a thermally created high pressure system over the oceans. This one's the Bermuda High. This one's the Pacific High. Again, they're formed from relatively cold ocean waters compared to warming surfaces during the northern hemisphere summer. This thermal low is created by the southwest deserts getting extensively hot during the course of the summer, so hot that they create a thermal low. Around a thermal low in the northern hemisphere, winds turn counterclockwise. This helps bring a lot of Gulf of Mexico moisture into Boulder area during the late summer. This thermal low is created over the Tibetan Plateau, a high elevation area that absorbs a lot of solar radiation throughout the summer, creating a thermal low. And again, counterclockwise circulation around that, pulling in Indian Ocean moisture into the foothills of the Himalayas, creating tremendous amounts of rainfall there. Looking at the winter hemisphere, we see that Australia's cooling off. The land surface cools more efficiently than the surrounding ocean, making it relatively cold, creating a thermally created high pressure system. Here's January, again, northern hemisphere winter, southern hemisphere summer. Now, if we look over the oceans in the southern hemisphere, we'll find that the oceans are relatively cold compared to the warming land surfaces, and you get much stronger high pressure cells. Around high pressure in the southern hemisphere, because the Coriolis force switches sign, air rotates counterclockwise around high pressure anomalies. Again, high pressure is formed thermally here as a result of a cold ocean next to relatively warm land. Around the equatorial zone, you have a tremendous amount of accumulation of heat, causing a thermal low over the Amazon, and also one over the Congo Basin, as well as one over Indonesia with very warm waters there. Moving to the northern hemisphere during our winter, you can see a Canadian high here. This is because the land surface is covered with snow. It's very cold compared to the surrounding waters. You get a thermally created high pressure system there, rotating clockwise. The same kind of system exists over Siberia, although more pronounced. Very cold here, creating a very pronounced thermally created high pressure surface. And again, clockwise rotation around that, but also out from that. The Aleutian low here is formed as a result of relatively warm surface waters compared to really icy and cold land surfaces. So you get a thermally created low pressure system there, rotating counterclockwise. The same kind of cell exists over the Iceland waters here, the Icelandic low. Relatively warm water surrounded by cold land surfaces creates your thermal low pressure there. These semi-permanent highs and lows add another level of complexity to the simple three-cell model that we described in a previous lecture. Now that we have an understanding of the three-cell model, the meridional circulation, as well as the position of these semi-permanent highs and lows, we can start to understand the main circulations in the atmosphere. Let's start off with the Aleutian low and the Icelandic low. Here's the Icelandic low, the Aleutian low. Air is going to flow counterclockwise around those thermal lows, forcing air to come up from the south on the right side of them and come down from the north on the left side of them. That changes the climate for those regions surrounding those lows. People in California are well aware of the fact that there's relatively high pressure off the coast, especially during their summer when the ocean's pronouncedly colder than the land surface. That creates a northerly wind that helps keep the summer relatively cold because that wind's taking more Arctic air and moving it down the coast. This also, we'll find out, helps support upwelling in the oceans and keeps the sea surface temperatures pretty cold there as well. Here's the Bermuda high. This is actually a very important player for steering hurricanes that tend to form off the coast of Africa. As they move in the trade wind circulation, sometimes they'll get pushed over towards America as a result of being forced to go around this large semi-permanent high pressure system that exists in the middle of the Atlantic. Down here we have those three high pressure systems that exist because of relatively cold ocean water, and they're going to force the winds to go in a certain orientation counterclockwise around them, giving relatively cold polar winds coming along the coast, the west coast of Africa, and also along the west coast of South America. Both of these winds are actually going to force upwelling, really cold water at the surface, and actually help support coastal deserts there that we'll look at later in this course. Now this graph also shows some very strong surface currents around the globe. For instance, the Gulf Stream here moving a lot of heat towards the pole and influencing regional climates. I'm going to save the discussion of the regional climate effects from these currents to Chapter 6 when we look at the oceans. The last thing shown in this graph is the intertropical convergence zone, its northward position during Northern Hemisphere summer, and its southward position during Southern Hemisphere summer, and we'll look at this in detail in a couple slides. Looking at our climate zones individually, first we have that intertropical convergence zone where the trade winds are converging near the equator. Now the position on annual average of the ITCZ is a little bit north of the equator, and this is because there's more land to heat up in the northern hemisphere than in the south. This is an area, again, with low surface pressure, ascending air forced by that convergence. Ascending air is forced to reach its dew point, and as a result you get clouds and precipitation. This graph shows that there's mostly easterly winds here. However, right at the ITCZ, where most of the air is simply rising, this is called the doldrums because there's not a lot of horizontal wind movement. Next, looking at the subtropics, this is an area where there's high pressure at the surface. It features descending air. Descending air, again, compresses and warms, causing the relative humidity to decrease. This is why some of the world's largest deserts are located at about 30 degrees north, like the Sahara, or 30 degrees south, like the Great Deserts of Australia. Equatorward of this area, you have the trade winds, which again, air that's trying to go down towards the equator gets turned to its right, giving you those northeasterly trades in the northern hemisphere. Right at the position of where the air is sinking, at 30 degrees north roughly, you don't have a strong surface pressure gradient there. There's not a lot of horizontal wind movement, and sailors in the old days called this the horse latitudes, because if they found themselves sailing there without any wind, they'd have to unload their horses into the ocean in order to limit the amount of drag and actually get somewhere. In the mid-latitudes, as we know, we have those two jet streams, which can help create high and low pressure systems and highly variable surface pressure as a result over time. There's increasing west winds with height in this 30 to 60 degree north or south band. Now this graph shows a thermally indirect circulation, which is known as the Ferrel cell, or sometimes called the mid-latitude cell. And it is something that comes out in the statistics if you average over enough time. However, I tend to overlook it in my classes because it confuses students. The reason why, if air is coming aloft, heading towards the equator, that would turn it going east to west. That would mean you'd have an east to west wind aloft, which is not what's observed in the mid-latitude. Instead, we have a very strong westerly winds aloft. So in taking such a long-term average, the Ferrel cell doesn't really give you a lot of insight into what happens day to day over the mid-latitude, which is again a function of the jet stream spinning up storms and also increasing westerly winds with height. The polar regions, as we know, features uplift along the polar front, air coming towards the pole, sinking, high surface pressure at the very poles, surface divergence of air that diverging air head towards 60 degrees north or south. In the northern hemisphere, it gets turned to its right, not well drawn in this graph, and you'll actually end up with a weak easterly wind there. This graph is looking at the position of the ITCZ during the southern hemisphere summer. What's shown is that it gets dragged much farther south over the warming land surfaces than it does over the oceans. And this is a function of the land surfaces being able to be warmed more quickly over the course of a season than the ocean is. In the northern hemisphere summer, same effect. The ITCZ gets pulled up to the north, across Mexico here, up along the southern border of the Sahara, and along the Himalayan foothills as well. It does not get pulled as far north across the oceans because the oceans have high thermal inertia. They're hard to warm up over the course of a single season. How the ITCZ affects what are called monsoons, which are seasonal wind shifts over a region, is interesting. So what happens, as air rises over the ITCZ from the surface aloft, air must converge to replace that rising air. What typically happens during their warm season, a land surface gets so warm, the air rises, it comes off the ocean to replace that, so you have an influx of moisture coming in during your monsoonal or warm season. So here we're looking at the Congo, where there's a flux of moisture coming in off the surrounding oceans over Africa. It's certainly coming in strength over Indonesia and Australia. And during the cold season, their relative cold season, northern hemisphere summer, you actually have cooling air here. You have high pressure developing over the cooling Australia, and air evacuates that region. So a very strong seasonal wind shift known as a monsoon. Like I said, the monsoons are typically warm season precipitation as shown here. A place we should highlight is what happens in the Himalaya, which has the world's largest monsoonal season. During their warm season, they have a lot of warmth happening over the Tibetan Plateau, which gives you low surface pressure. Air's rising there, so to replace that air, it comes in off the Indian Ocean. As it comes in, it converges over a hot plate, so to speak, over a warm surface, which helps push it upwards, forcing clouds of precipitation. But also the land surface is rising here as you go towards the Himalaya, so you have an orographic component. These are places where the world records rainfall of about 1,000 inches in a single year, mostly as a result from this monsoonal precipitation during their warm months. The pattern completely reverses during their winter because that Tibetan Plateau cools off so effectively. It creates thermal high pressure. Air tries to evacuate the high pressure, and it does so. Goes down the foothills. As it's coming down, it dries. The relative humidity must be reduced as it goes down from compressional warming. So you get almost no rain during their dry season, and the wind flow pattern goes the opposite direction. So again, the monsoon is a seasonal wind shift here coming from the south during their warm season, going from the north during their cold season, but typically it's associated with warm season precipitation because it attracts oceanic moisture to that low pressure anomaly. Many places that aren't at the extreme limits of the ITC's position north or southward get 2 rainy periods per year, as the ITCZ has a chance to run over them twice. Here, the ITCZ is heading to its northward position, gives them a bump of rainfall, and as it hits its northward position and heads back south, it runs them over again, giving them a second mode of rainfall. This animation is pretty good. We can show the ITCZ here shown in July, but we can shift the season too. And this is what we just talked about, that the ITCZ migrates further over land than it does over the ocean as a result in the difference in thermal inertias between the two. We can also show the position of the Hadley cells. And again, where the Hadley cells converge is what the definition of the ITCZ is. And we're looking at the meridional average here. What this instantly brings out is that not only does the area of uplift have a seasonality to it, also the area where there's descending air has a seasonality to it. That means that some areas which might have very dry conditions during a certain season, when the descending branch of the Hadley cells over them, might get the ITCZ to come over them during a different part of the year. So that dry zone migrates north and south, as well as the wet zone associated with the ITCZ. Also shows the polar front, and it has a seasonality too. And this is the area that is often associated with the most precipitation in the mid-latitudes, as subtropical air is forced to rise up over that polar front. We can also show our semi-permanent highs and lows and their seasonality. So I'm going to turn off those guys for now. And this is kind of nice. You can see our July with our very strong subtropical highs over the oceans because they're relatively cold. We see that really pronounced low over the Himalayan foothills associated with heating of the Tibetan Plateau. And then we can move back again to January. And then we can see again in the southern hemisphere summer, we see this really strong Icelandic low, really strong Aleutian low, etc. To show the impact of the ITCZ's position on precipitation, simply turn both those buttons on, and we can look at that seasonality, that the maximum precipitation in the tropical zone definitely follows the ITCZ. Going further, turning on the Hadley cells, you can also find that the dry zones typically follow the descending branches of the Hadley cells. Key points from this final section of Chapter 5, semi-permanent highs and lows are created thermally. Places that are cold for an extended period of time over a season tend to make high pressure. For example, Siberia in winter. Warm persistent anomalies tend to make low pressure. The ITCZ, the ascending branch of the Hadley cell, follows the maximum surface heating, so it migrates with season, heads north during northern hemisphere summer and south during southern hemisphere summer. It migrates more over land than ocean due to the differences in thermal inertia. Wherever the ITCZ goes, it tends to rain a lot, causing monsoonal precipitation, or warm season precipitation. The descending branches of the Hadley cells are quite dry, and they also have a seasonality, so that dry part of the globe migrates north and south with the cells themselves. All these wind circulation effects give us a first-order look at regional climate forcing, both temperature-wise and also precipitation-wise. However, we must look into the oceans for further guidance as well.